Okay, good morning, everyone. Just a few announcements before we get started. So the projects are now online. Remember, these are individual projects. You are allowed to discuss with your classmates, about general things about the project, but all of the work should be your own. Okay. There is the versions that are on that I put on Canvas are correct, but it's just pointed out to me that there is a typo in the one on Crowdmark. Just to make sure you're aware. I will update this after class, but just to make sure you're aware. In the invasion dynamics for Y, it currently says this minus GM, dym. This term here should be AM. Okay, so just in case you've taken the version that's on Crowdmark, I will update it, but please be aware that this should be an AM. Okay, so that was the first announcement. Yes.
It seems to be a GM in the second term.
This should be a DM. The GM. I'll be GM. Yes. Is that on there?
I think it is GM.
Yeah, I've got GM. Yeah, sorry. I forgot to add that when I wrote that. So this should be the correct one. Anyway, I will double check that it is all correct on the versions I've
DM correct also?
Sorry?
Is DM correct? It's not on the updated one.
Is there a DM?
It's on
I
DM.
think it's just the master.
Oh yeah, sorry, I'm thinking of a question I was going to give you guys later. There we go. This one should finally be the right version. Apologies, I don't have the sheet in front of me. So, but yeah, I will update the version on Crowdmark and I'll send out an announcement just to make it clear that this is the one that is on there will be the correct version. Okay, the one on Canvas is correct. Okay, so that was the first announcement. The heat gets to me, you can see. The second announcement is Wednesday's class is going to be a little bit different. On Wednesday, we're going to be going through how we can simulate evolution. This is part of the projects as well, that you're going to be tasked with doing some simulations. So you have to write some code yourself. You can use ChatGPT and things like that to help you. I'm not going to stop that. But ChatGPT and things like that will probably be limited in how well they can help you do those things. So Wednesday, we're going to go through, in the first part, I'll go through some general methods for modeling or simulating evolution. And then in the second half, it's going to kind of function as a workshop. So bring like laptops or iPad, something that you can code on. And there'll be examples to work through. And basically, I'll just go around the class and help you get familiar with how we simulate evolution. Okay, so obviously, no, you don't have to attend that, but I wanted to give you guys an opportunity to work through examples and get familiar with simulating. So yeah, bring your tech on Wednesday. I think that's it for announcements. Okay, today we are going to be talking about evolutionary branching. So I've mentioned this a few times already, but we've never actually explored it in any detail. We've been focusing on adaptive dynamics in the last few weeks, which you're familiar with now. And we've been looking at, for example, how do we find singular strategies, which are momentary stationary points, if you like, in an evolutionary process. That's where your selection gradient is equal to 0. So at that point in time, nothing is happening in terms of directional selection. And we then look at higher order derivatives around that singular strategy, telling us whether it's convergent stable. In other words, is it attracting? Do we move towards it? And is it evolutionarily stable? Is it a fitness peak? Okay, and then we can have these as combinations, all 4 combinations of evolutionary stable or unstable and co-evolutionary stable, convergent stable or unstable, which gives you 4 possible types of singular strategies. And we focused really so far on continuously stable strategies, ones that are both convergent stable and evolutionarily stable. So those continuously stable strategies are kind of nice because they are these evolutionary endpoints. Once you get there, nothing else can invade, and there is a path that will lead you towards that through small mutations. So this endpoint, you kind of get there, you stay there, okay? But that's not the only type of outcome we can have. If we have something that is convergent stable but evolutionarily unstable, then you'll move towards it, but then we'll go through this process of evolutionary branching, which creates now two phenotypes that coexist together. Okay, so we're going to explore this today. This emerges through a process that's known as disruptive selection, so we'll talk a little bit about that. Other than that, there's not too much new terminology. For ease, I'm going to stick with this intraspecific model of competition that we've looked at a few times. So just a quick reminder, you should all be familiar with this by now. Ni is the population density of phenotype Xi. Aij is the strength of competition imposed on an individual of phenotype Xi by an individual of phenotype Xj. Ki is our carrying capacity for a population that is in principle entirely composed of individuals of phenotype Xi. And then R, which we're going to assume is positive, is our intrinsic growth rate. And this assumption here ensures that our residence ecological equilibrium, when we just have one phenotype in the population, it tends towards Ki. Okay. So we've been through this model a few times. And one of the things that we've established, first of all, is that like I said, if R is greater than 0, then we have a locally asymptotically stable equilibrium at the carrying capacity Ki. And then that means we can use adaptive dynamics to write down our invasion fitness of a rare mutant at that carrying capacity. And for ease, I'm going to write, usually I write XR for my resident. I'm just going to write X from now on, just to drop the subscripts. You should be familiar with the fact that this is a resident type thing. Okay, so what is my invasion fitness? Remember, this is an invasion fitness of a rare mutant with phenotype XM in an environment created by a population that has phenotype X. So this is the per capita growth rate. We don't have to use the next generation method for this example here because there's just one equation that's going to describe my dynamics, which is dnm dt. We take the per capita growth rate of this population, so that's why we divide by nm. And we evaluate this when our resident population is at its carrying capacity, at its ecological equilibrium. So if we do this, we end up with R times by 1 minus A of xm x. So that's our competition imposed by our resident on our mutant strain, times by n star, which in this case is just going to be K of x, carrying capacity for our resident population, and then divided by K of xm, so the carrying capacity for the mutant population. This is what we've done before, so there shouldn't be anything new here. Just a slight change in notation. Okay, you should all be familiar as well with calculating the selection gradient now, which I call S of x. So we take the first order partial derivative of our invasion fitness with respect to our mutant trait, and then evaluate this at the residence trait. Remember, we do this evaluation step after we've taken the derivative. So what do we have here? Well, note that we've got xm's on both the numerator and the denominator, so we're going to have to use the quotient rule. We have a minus r. This K of x here is just going to be a constant, so that can come out the front. So we're going to have minus r, that's by K of x. And then here, I'll do the, let's see. Take the derivative, no, let's take what's on the denominator, K of xm. In fact, I'm just going to do the substitution step straight away. So we'd have K of xm, which we're going to evaluate at x, so that becomes K of x. We take the derivative of the competition function, A. We're taking the partial derivative of this with respect to xm, and we evaluate this when xm is equal to x. And in the second part, we're going to have A. We're going to evaluate this at xm is equal to x. So we have A of x. And then we take the derivative of the denominator. So we have K prime of xm. And again, we evaluate this at xm is equal to x. So this is just the quotient rule. So I'm doing here. And then divide by what was on the denominator squared. And we evaluate this at x. So K of x squared. Was that clear for everyone? Just the question. Okay. So what can we learn from this? We can do a little bit of simplification. I guess we can take the second term, it's got a minus sign in front of it. There's a minus sign on the outside, so we can bring that on the outside. We have a k of x on the outside as well, so we can do some cancelling. So here we're going to have our first term will be a of xx. We'll have a k prime of x, and then divide it by, well, here we had k of x over k of x squared, so it's just going to be k of x. And then here we had a k of x squared and a k of x squared, so they're going to cancel. So here we're just going to have the partial derivative of a with respect to xm, evaluated when xm is equal to x. So we've done this before for our selection gradient, but we did it with particular choices for our carrying capacity function k of x and our competition function a. Any questions so far? Okay, so we're going to make a couple of assumptions at this point. And these are fairly generic assumptions that we make. They're not, there are cases where we might not want to make these assumptions, which I'll discuss in a second. The first one though is we're going to assume that competition is symmetric. Okay. So what this means then is that the only thing that really matters is going to be the distance between our phenotypes xi and xj is going to determine our strength of competition. So this is a reasonable assumption, say if we're talking about some kind of preference, or there's kind of like an equal there's an equal value to the resources that they're competing for, perhaps. I talk about preference, suppose they prefer a particular, as birds, and they prefer a particular type of seed. There might be different types of seeds in the environment. Birds that prefer similar seeds are gonna compete more strongly, and it doesn't really matter if a bird prefers a medium-sized seed. If there's a bird that prefers a slightly larger seed or a slightly smaller seed, we're kind of assuming that if it's a similar distance in terms of their preferences, then it doesn't really have much of an effect. Okay, it doesn't matter whether it's competing for a smaller one or a larger one. It's just the distance that matters. Okay. So we have this symmetry here. We might always not always have that symmetry in terms of, maybe there's more value to those larger seeds. And so the competition might be asymmetric, but here we'll just assume it's symmetric. We're also going to assume the competition is strongest for individuals with the same phenotype, and without loss of generality, we're going to assume that individuals who have the same phenotype X here have competition 1. Okay, so the strength of their competition is just going to be 1. So essentially, we just normalized this competition so that it doesn't exceed 1. Again, you can have scenarios where it might be greater than 1 or less than 1, but really, for the purposes here, with this assumption here as well, this kind of just becomes like a normalization set. So that means up here, we think about this equation now, this a of xx is going to equal 1. And because the distance, I haven't actually got this assumption on here. Well, actually, no, technically it's kind of that. Because the distance is the only thing that matters, we need to have some function that essentially peaks at a of xx equal to 1. Okay, so for example, we might have a function, I'll draw a Gaussian, that looks something like this. This is my distance, I'll call it xm minus x. My a of xm maybe looks something like this. It's a of xm x. And we're going to assume that this peaks at 1. So because this is a peak at 1, my partial derivative of a with respect to xm, when xm is equal to x, is going to equal what?
Shouldn't it be zero then?
We're at a peak, just like any function, right? So this term here is going to equal 0. Note that this here is just this here. So that means that my selection gradient initially in this population that I'm starting with, my monomorphic resonant population, my selection gradient is just going to reduce to the first term, r times by k prime of x over k of x. So what do you notice about this selection gradient? Considering we've defined this carrying capacity, we've defined this competition function, and this is telling us when we start off, this initial population, there's only one type, and then we're introducing these mutants. We're seeing what happens to the direction of selection. In other words, how this population is initially evolving. What does it tell you that's important?
It depends entirely on the carrying capacity and its ratio.
Yeah, and what's missing basically from this? The competition. Okay, so the competition function, because of this, essentially because we're assuming these like very small mutations, we're always basically up here. So at a point where there's just one individual type in the population, one phenotype, the competition really doesn't matter. Like a tiny change in this competition doesn't really have any effect in terms of directional selection. Everything's being dominated now by this term here. So by the carrying capacity. And it depends, the direction of selection. So this carrying capacity, by definition, the denominator has to be positive, right? Because it's a carrying capacity. R has to be positive as well. So the direction of selection depends entirely on this k prime, so the gradient of my carrying capacity at a particular point. So intuitively, like I said, although a mutant will be slightly further away from, by definition, it will be slightly different from its resident, its competition function, a of xm of x, is always going to be less than a of xx, which is equal to 1. Although this is always true, this is always going to be a very small effect. And this is a very small effect. It'll always going to be an effect of second order because this derivative is equal to 0. Okay. So later on, we have to think about the second order derivatives, but initially, as this population is evolving to start with, we don't have to take that into account at all. Like I said, the direction of selection is therefore solely determined by the gradient of carrying capacity. Yes.
Sorry, could you just explain the inequality again? Like why we know that?
This, because we're assuming up here that competition is going to be strongest for individuals with the same phenotype. So, and we're assuming that this strength of competition is 1. So that has to be my maximum over here.
Right.
So for any mutant is going to be different from X, it has to be away from that peak.
Yeah.
So the competition imposed by this resonant on this mutant has to be less than the competition between resonant types. Yeah. Okay. Okay, so what can this tell us? Well, we can go through, the standard thing of find our singular strategies, find our evolutionary stability, find our convergent stability. We'll do a certain amount of that. But we can actually kind of skip ahead a little bit and just kind of intuitively understand what's going on in terms of convergent stability here, because the direction of selection, I'll just go back up here for a second. The direction of selection is going to be positive if k prime of x is positive, and it's going to be negative if k prime of x is negative. Yeah. So what's really going to happen is the direction of selection is just going to follow this carrying capacity function, and the trait x will increase if k prime of x is positive, and therefore it's going to track this k prime of x. Okay, it's not going to be exactly the same because of this r and this k of x here, but it's going to have the same sign. Therefore, the direction of selection is just going to follow up until we get to a peak of this k prime of x, if one exists. In principle, that k prime of x could go off to infinity in a mathematical sense, but really it should just go off to some peak. An environment can't support an infinite amount of individuals. Therefore, we'll just follow this until we reach a peak. So that peak is going to be a singular strategy. Sorry, yes.
I just had a question
Yeah.
about, K of X. Earlier you mentioned that we said it was constant while we were looking at the fitness. No, I'm sorry, invasion fitness, you mentioned that K of X is constant.
Yes, K of X is constant here in terms of this, with respect to this derivative of XM. So yeah, when I said that this was constant, we can treat this as a constant because we're taking the derivative with respect to XM.
Right.
But in like K of X is not a constant function, it's just K of X is not a function of XM. So yeah. Okay, so what was I? So our selection gradient, like I say, is going to follow our carrying capacity here. And it will reach the same maximum, or rather, sorry, it will reach the same, or have a maximum, the same value of X as K prime X. Okay, and we know that we're going to evolve in the direction of our selection gradient until we reach a singular strategy. So that singular strategy X star, if one exists, is going to be the same for our selection gradient and our carrying capacity function. So we know that K prime of X star must equal 0, and this is going to be equal to our selection gradient at X star. Okay, so what we can do is we can think a little bit about what happens if we take the derivative of our selection gradient with respect to X. I mean, it's just a function of X, it's not a function of X and XM, remember, this is just a one-dimensional function now. We take our derivative of our selection gradient with respect to X star. Sorry, with respect to X and then evaluate it at X star. So again, we need to apply chain rule. We're going to have an R out the front. And all we're doing is we're taking the derivative of this here. So when I do that, I'm going to have K of X times by K double prime X. Divided by AX squared minus, we can have K prime of X times by the derivative of the denominator, which is K prime of X. We're going to have minus K prime of X squared. And this is being evaluated when X is equal to X star. So we can split this out. We'll get R times by K double prime of X over K of X. And then minus K prime of X over K of X all squared. And again, evaluated at X equals X star. Can anyone tell me what's going to happen to the second term when I evaluate this at X equals X star? In other words, this term here.
It'll go away.
It'll go away, yeah, because we've got up here that K prime of X star is equal to 0. So at the singular strategy, we're going to have R times by K double prime of X over K of X. And logically, what sign must this have? Sorry, this is at X star. What sign must this have? It's going to be positive, negative, or equal to 0. Negative? Why do you think it's going to be negative?
Because the first derivative is 0,
Mm-hmm.
so the second derivative should be negative.
And what does the second derivative of negative being telling us about a general function, right? It's a peak, right? It's a maximum. And we know that we're going in the direction of our selection gradient has to be the same as the direction, or the gradient of our, the same sign as the gradient of our carrying capacity, right? So if our selection gradient is kind of climbing this peak until we get to this peak when this carrying capacity has gradient 0, that's the same point at which our selection gradient is equal to 0. Therefore, it must be this can't be a peak and this be a minimum, right? This can't be a max and this can't be a min, or vice versa. They have to both be a maximum because we're going in the direction of our selection gradient. So it initially leads to local maximization of K of X. Again, remember, the competition is having essentially no effect on things in terms of evolution. So logically, it has to be convergence stable. Like I said, we could have gone through the slightly more laborious process that we normally do, but you can also argue it intuitively this way in this particular case. Okay, note that you can't necessarily always do this in a general case for like other types of models, but for this particular type of model, because we had this relationship here, we were able to say, well, the selection gradient is going to have the same sign as this, therefore it has to peak at the same point as this, if it has a peak, okay? So just a word of warning, careful about applying that logic in general, but in this particular case, we can. Okay, so we know it's convergent stable. We can work out its evolutionary stability in the classic way. So remember, we can calculate our evolutionary stability by taking our second derivative of invasion fitness with respect to our mutant, and then evaluating both our mutant and our resident after this at our singular strategy. This is kind of a laborious, it's not terrible, but I don't want to waste too much class time just calculating derivatives every time. So I am going to give you the answer, but feel free to work this out in your own time for practice. We have, again, this R on the outside. Note that because R is positive, essentially R has no effect on any of the evolutionary dynamics here. It just scales the time over which things occur. It doesn't determine anything to do with stability. So the R factors out. Turns out here that we are going to have K double prime of X star over K of X star. Note the similarity here. This is the same condition up here, actually. This term here is the same as what we had for our derivative, telling us something about convergent stability here. So that happens to be the same. And we're going to have our second order partial of A with respect to xm evaluated at X star. And for this point X star to be evolutionarily stable, remember, we've not actually found what X star is here. This has to be less than 0. Okay, so we've got some different terms here. We can just analyze them. Note that we've already figured out that this term here has to be negative. Or at least the numerator is negative and the denominator is positive. So this first term here has to always be negative. This term here should also be negative, because the strength of competition, remember, we're going to be at a peak, right? When xm is equal to x. This is a two-dimensional function. We're evaluating, we're going to have a of x star essentially, which a of x star is going to equal 1. It's a peak of this function, but we don't know anything about the second derivative. Well, it has to be a maximum, right? Because we're saying that that's the strongest competition. So this has to also be negative. So that means that depending on the magnitude of these functions, the whole thing could be negative or positive, right? Because of this minus sign. Something negative minus something negative could be positive or negative, depending on their magnitudes. That means that we could have evolutionary stability if this is 0 or less than 0, or we could have instability if it's greater than 0, and we know that it's convergent stable already. So really, what this is saying is that depending on the magnitude of this function here, when it's evaluated at its peak, essentially the strength of the curvature of this competition function will entirely determine, relative to this, how whether we have evolutionary stability or instability here. Yes.
So we can't actually say it's less than 0 then in the blue or the.
Oh yeah, sorry. This is saying the single strategy is evolutionarily stable if this is true.
Oh, right.
But yeah, in principle, it could be stable or unstable.
Right.
So this condition is not always satisfied.
Mhm.
Is the point, yeah. Okay, so let's go through an example. That's the basic principle of this model. Let's assume that our competition function is going to be given by xi and xj, two phenotypes. They look very similar to what we've had before. We can have an exponential with xi minus xj in brackets all squared. We're taking minus that. So this is our distance essentially squared. And then we're going to divide now by 2 sigma of alpha, sigma sub alpha. This is just telling me that it relates to, sorry, sigma sub a. That'd be less confusing. Sigma sub a squared. So this is just a Gaussian, right? This is like a bell curve. And this sigma a, in fact, I've called it sigma alpha, I swear, so I'll just call it sigma alpha for ease. There we go. Sigma alpha is positive, and it's telling you about the standard deviation. Okay, so it's telling you something about the width of this bell curve. And we're going to assume something similar for our carrying capacity. Now it's just a one-dimensional function. We're going to have k hat is just some scalar. The k hat doesn't affect the stability at all here. It just scales the total population size. And here we're going to have minus x squared over 2 sigma k squared. So previously we've analyzed this model when the denominators were both equal to 1. So now we're essentially just looking at a slightly more general version of this. Okay, so we know from the selection gradient that there's a unique singular strategy when k prime of x star is equal to 0. It should be pretty obvious if we were to take our derivative of this, we're going to end up with a 2x out the front. This is only going to be equal to 0 when x is equal, the derivative of this is only going to equal 0 when x is equal to 0. So we have one singular strategy here, x star is equal to 0. We know that this is convergent stable because of what we discussed earlier. And we had a condition above for evolutionary stability, which looked like this. So we had k double prime of x star over k of x star minus second order partial of a with respect to x m evaluated at xm and x equal to x star. And this has to be negative for us to have an evolutionarily stable singular strategy. So now we can just substitute in our functions. Note that our functions above, these two functions here, are essentially of the form g of x is equal to e to the f of x. So if we take our first derivative of this, we're going to have f prime of x e to the f of x, just by the chain rule. And then our second order derivative, we will have an f double prime of x plus an f prime of x squared times by e to the f of x. Okay. And for our model here, we've got f of x is equal to some, in fact, I'm going to call this something different. I'll call this f of y, just so we're not confusing things. F of y is going to equal minus y squared over 2 sigma k. F prime of y, therefore, is going to be minus y over, sorry, I won't call these sigma k's. I'll call these this should be, let's just call this 2 sigma squared. I want to try and just illustrate what I'm going to do quickly on the left-hand side with generic functions on the right-hand side. If I take the first order derivative of this f of y, I'm now going to end up with minus y over the 2 will come to the front and cancel. So we'll just end up with over sigma squared. And then the second order derivative is going to be minus 1 over sigma squared. Okay, so if we put all of that together, we can just substitute in what we had already. So if we take our second order derivative of k, we're going to end up with a k hat out the front. We will have over this this side, we will have an e to the minus xi squared, or rather this should be x star squared, is the x star squared, over 2 sigma k squared. I have something as well in the brackets, yes?
Sorry, k hat is a constant, it's not a unit vector, right?
Is it a constant? Yes.
Okay.
On the denominator, we're going to have a k hat e to the minus x star squared over 2 sigma k squared. We're actually evaluating the x star as equal to 1 anyway, so these are going to disappear. So we can actually just ignore all of those terms there. From what we've learned here on this right-hand side, we'll have this second order derivative of our function that was in the exponent plus the first order derivative squared. So we'll end up with an x star squared minus sigma k squared over sigma k to the fourth. And then things will look very similar on the right-hand side. We'll have in brackets an x star squared minus sigma alpha squared over sigma alpha to the 4. And then we'll have e to the 0 over e to the 0. Again, these are just equal to 1, so we can ignore those. The x stars, because we're evaluating this at x star is equal to 0, those are also going to disappear. Yes?
That sigma k in your first term, is that squared or no?
Yeah, it is. Sorry. Just dodgy writing, that was all. Square that. Okay, running out of room a little bit on this slide, so I'm just going to zoom in. This simplifies down essentially, so we're going to have this squared term here is going to cancel here. The squared term on the denominator. That whole thing will cancel. That whole thing will cancel here, and again we'll have a squared term in the denominator. So we're going to end up with 1 over sigma alpha squared because of this minus we've got here, because this minus 1 over sigma k squared has to be negative for us to have an evolutionarily stable singular strategy. In other words, we need sigma k minus sigma alpha to be less than 0. In other words, if sigma k is less than sigma alpha, we have a CSS. In other words, it is both convergent stable, which we already know, and it's evolutionarily stable. But if sigma k is greater than sigma alpha, then we have a branching point, abbreviated BP. It'll be convergent stable, but evolutionarily unstable. So we've got a condition now, because we can just choose these parameters to be whatever we want, or more precisely, if we're thinking about a particular biological system, maybe we'll be informed as to what these parameters are. In principle, there's no reason as to why we should be in this scenario versus this scenario necessarily, right? So what does this all mean then? Clearly, there's some relationship that's important between these sigmas, which recall if they were part of our, if I just go back up here, these sigmas here were scaling our competition and carrying capacity functions. And because these are bell curves, they're scaling the width of them, essentially, so how wide they are. So it's having an effect on their standard deviation. If we were to try and think about what is a biological interpretation of this, then let's have a quick sketch of what these two functions might look like. And I'll sketch this as xm minus x star. So they'll both peak at 0. So this is the point where xm is equal to x star. And suppose we have a carrying capacity function that looks something like this. My k of xm. And we can think about this as, okay, so this is a sketch. It has some parameter sigma k, which is telling me something about how wide this is. The bigger this sigma k is, the more this bell curve gets stretched out, right? The smaller sigma k is, the more narrow this gets. So for us to have branching, we need our sigma alpha, which is, again, we've got a bell curve describing these functions. We need our sigma alpha, which again is telling me something about its standard deviation, about the width of this function, has to be less than sigma k. Whereas if our sigma alpha is greater than sigma k, suppose it looked something like this purple dashed line here, that would be a case maybe that's like this, where our sigma alpha is greater than our sigma k. So what this means then is that at our optimal carrying capacity, when, because that's what we go to originally, that's where we evolved to, x star is equal to 0 in this case. The strength of competition between, the strength of competition experienced by our mutants at that singular strategy, that function must decrease faster than the carrying capacity decreases. So essentially it's saying that at that point, the effects of competition are decreasing faster than the effects of the carrying capacity changing. Remember, we're always talking about a mutant is invading, has a slightly different competition, and slightly different carrying capacity function to our resident type. Basically saying we need to be in this green scenario here, this competition strength must decrease more rapidly than the change in the carrying capacity decreases. Because we're always starting, if you think about at this singular strategy, we've evolved to this singular strategy, we're at a peak for our carrying capacity. So any mutant is going to have a lower carrying capacity than our resident population because we're at a maximum to start with, right? Because we're at the singular strategy. So it's going to necessarily have a smaller carrying capacity. It's less efficient perhaps at using resources than the resident type. So if its competition doesn't decrease enough to compensate for that, then it's not going to be able to invade. So all this is saying is that this drop off here in this green curve has to be stronger than the drop off in the red curve. So its loss in carrying capacity has to be more than offset by its benefits that it gets in reduced competition. So that's essentially the biological interpretation of what's going on here. Okay, so what happens next then? So remember that our selection gradient was only determined by our carrying capacity. The competition function had no effect there. And that was because we had this d of a with respect to xm, whenever xm was equal to x is going to equal to 0. So we evolved this singular strategy. We're attracted to it because it's convergent stable. But once we get there, our invasion fitness is actually now a minimum. These second order effects become important. And so our invasion fitness of any mutant, any mutant xm near to our x star is going to look like something like this. So this is my xm varying along the horizontal axis. Suppose my x star just happens to be here. I know we typically had it, it's 0, but I'm just putting it over to the side here just so it's a little bit clearer what's going on. Our invasion fitness now needs to look something like this. Okay. If we've got a case where competition is falling off faster than changes in carrying capacity are falling off. So our second order effects are now important. So imagine we've got a mutant, it's maybe over here. Maybe we'll call this XM1, or we've got a mutant over here, XM2. These both now have higher fitness, and so they can invade. You recall when we did our pairwise invasion plots, I'm just going to zoom in here a second so I can sketch this. Pairwise invasion plot for this kind of scenario looked like this. We had our resident trait, sorry, so our resident trait here and our mutant trait. That's our 45-degree line of xm is equal to x. If we had a scenario that looked something like this, this is a plus region, and this is a minus region. This is my singular strategy here. We converge towards this singular strategy. Sorry, that should be this way. We'll converge towards this singular strategy, but when we get there, remember, if we can draw a vertical line through this singular strategy that is always in this positive region, either side, then that means that mutants here or mutants here can invade. They can invade on both sides. Therefore, we have this process that's called disruptive selection. So these two mutants now, they're going to be able to coexist. And they're going to be able to invade. Now, the next few slides, I'm actually going to skip over today just because we're running out of time. These are less important things in terms of the material, but here these are kind of included for completeness, if you like. So at this point now, if you think about it, we've now got two resident strains because we've got something going on this side and we've got something going on this side. So now if we want to look at what happens to a rare mutant, we need to think about, well, is the rare mutant over here or is it over here? So after they've branched, what happens? Well, we need to actually think about the resident dynamics of these two mutant strains, X1 and X2, and then is a mutant over here or is a mutant over here? So we can then write down an equation for invasion fitness in terms of invasion fitness for a mutant at resident trait 1 or resident trait 2. We can then go through the same process again of calculating the selection gradient at each of those resident strategies. This becomes quite involved. I'm not going to go into this. There's also a way, you can write down what is ultimately the singular strategies for those types. So there is a process that one can go through. Essentially, you're just doing the same thing, but it's more complicated now because now we've got two resident types. We need to think about where our mutant is appearing. Okay. The thing I wanted to end on though today is that we can simulate this. So this is what's going on in this model here. This is our phenotype X, and we initially evolve up to our singular strategy X star is equal to 0. This red curve here, this red line, is telling me where my branching point is. Okay. So we can see at this point, this evolutionary trajectory splits into two. So although we've been attracted to this fitness peak here, once we get there, it's no longer a fitness peak. We have these mutants on either side can invade. This is where these second order effects of competition come in. They now branch out. This region of time, if you like, if we were to break this into different points in time, this would be what we've done up until now. What I just described a moment ago in terms of having to think about what happens if we've got both of these resident types in. We've got two types coexisting at any time point now. We now need to think about, well, how does a mutant do if it's over here versus a mutant doing if it's over here? Again, one can continue this process and calculate there are singular strategies, co-singular strategies on these blue lines, at which point here a branching event occurs again. Ultimately, in this type, we end up with 4 different coexisting phenotypes in this particular model. So why do we care about branching? Well, it's a process that generates diversity. We look outside and we see lots of diversity, see different plants and animals and things like that. How does some of that diversity come about? There are different biological mechanisms that can generate that. If populations get separated for long periods of time, they can speciate. You can separate into different species. This is a process that describes how, without that separation, we can get this branching into different phenotypes coexisting within the same population. Okay. you think about this, one way to think about this, if it makes it easier, is that these different phenotypes could represent, say, different strategies, thinking back to like evolutionary game theory. And so by separating into these different strategies, they're able to coexist, and they kind of self-organize into these patterns where they're kind of far enough away that they're balancing having weaker competition with the carrying capacity that might be lower. So the carrying capacity peaks at 0. So these guys here maybe are benefiting from having a higher carrying capacity, but they also face stronger competition. Whereas these guys over here have a lower carrying capacity, but they have weaker competition because they're much further away. Okay, so you can think about balancing these different strategies as a way to generate diversity and maintain that diversity within populations. Okay, that's it for today. This is the kind of simulations that we're going to be going through on Wednesday, and is the kind of thing that I'd expect you to be able to do in your projects. So please come along with your laptops or tablets, and we'll practice coding these things on Wednesday. Okay. Incidentally, I'll put up the notes for those 2 slides that I skipped over online. That, like I said, is really there more for completeness to illustrate what goes on. It's not something that I'm going to be expecting you to do in like the project. Okay.